Today we continue in our Chapter 7 lectures in 7.4 talking about geometrically defined vectors and applications. So what we see here on the left are some vectors, and what we see here on the right is one application of vectors. That is, a force is being applied to the river by the people who are rowing, and that force is also being acted on by another force, which is the river itself. So let's start with a review of vectors. Here we are in homework 20. I've said that for help with questions 1 through 3, see these pages in your textbook. And there's also a help video accompanying number 2. So I would recommend that you watch that. So I'll go over questions 1 and 3. Here we have some arrows, and each of these arrows is a vector. A vector has two things. It has magnitude, that is the length of the vector, and it has direction. So the direction of the vector matters very much. What does not matter is where the vector starts or where it ends. For example, if I were to draw vector u again, I could draw it anywhere I wanted so long as it had the same length. You see, the same length, and it had the same direction. So this pink arrow that I've drawn right here, even though it starts and ends at a different place, is also vector u because it has the same magnitude, the same length, and the same direction. So when we're trying to match together vector combinations, all we have to do is consider the length and the direction. So let's look at vector p. Well, vector p is going to be taking angle u and stacking 3 copies of angle u together. So now it's the same direction as angle u, but it's triple the length. And that's what we have here. 3 times vector u. Now, vector notation is usually written in 2 different ways. We usually see it either with the lowercase letter and an arrowhead that only has the top part of the arrow. That's commonly a way that we see vectors. And then sometimes we also see it with the arrowhead going both directions here on the arrow. And that's how you see it in this problem. But usually it's more common to see it either with one arrowhead only, or half of an arrowhead rather, or if you do see it with both, you usually see a bold letter. And these problems, they have them written a little bit closer to how I would expect to see a ray in geometry. But nonetheless, here are some common vector notations. Okay, so let's look at, we already said that vector p is the same as 3 copies of u. Now let's look at vector v for a second. Vector v has a length of 1 diagonal, and it's going in this 45-degree angle to the positive x-axis. If I were to take a similar sort of length, or exact same length, but go in the opposite direction of v is going downward at this diagonal, right? And so this would actually be negative v. So negative v occurs when you have the same length as positive v, but you go in the opposite direction. And so you see that q fits that description right here. Q is going in the opposite direction, but has the same length as v. So q is the same thing as negative v. So we looked at scalar multiplication with pink. We looked at the opposite, or the equilibrant. And next we're going to look at a vector sum. So let me go ahead and erase all this. It's getting crowded. For vector sum, let's consider u plus v. So if I have a vector, here's vector u, and I add to it another vector, oops, There's vector v. Think of this as two forces that are acting together. So think of this as, okay, let's say vector u represents a boat trying to cross a river, and vector v is the direction of the current. Well, where is the boat going to end up? The sum of two vectors is always going to be the parallelogram diagonal. Okay, so this would be u plus v. And we see that with r. So again, going back to the idea of the parallelogram, vectors can be added together by making the two vectors connect as two sides of a parallelogram. So just take the end of one vector and connect it to the beginning of another vector, and you have two sides of a parallelogram. So you can see the rest of the parallelogram. So here in purple I've drawn the rest of the parallelogram, and then in green I've drawn the diagonal of the parallelogram, and this is what's called the resultant vector. It's the same as the sum. So just as u plus v is the same thing as vector r, it's the same as the resultant. So a vector sum is known as a resultant. Now, when you go down to the next problem, question number 2, it gets a little bit more complicated, but there is a great video here that will walk you through the whole thing. So if the explanation from question 1 was not sufficient, you can watch the video. But if you can try to, I would recommend that you would see if you can match these up correctly without the video for starters. And don't forget that you can always click on the magnifying glass, and the magnifying glass will give you an enlarged graph. Alright, so question number 3 goes back to the vocabulary resultant. So we need to find vectors A and B. And here you see vectors A and B are in every single diagram. So the question is, which would be the resultant? Now the resultant, remember, is the same as adding the two together. So the resultant is going to be vector A plus vector b is the resultant vector. And a resultant is always going to be the diagonal of the parallelogram formed by vectors A and B. So what you should do is just see if you can finish a parallelogram using A and B. So if I were to finish the parallelogram, these two are not connected as two sides of the parallelogram head to tail. The two vectors are connected both together at the beginning. So that's not going to work. Even though this is a diagonal of a parallelogram, you need to have the two vectors connected head to tail, like here. Here you have A start, A ends. At the very end of A, then we see that B is added on. These two vectors are connected correctly, head to tail. And then A plus B ends up being the resultant because it's the diagonal of a parallelogram that would be formed. So this is one of them. That's good. Here also, A and B even though these are not connected head to tail, we can modify the diagram. If we draw another copy of B right on the end of A, and this would be the same as B because it has the same direction and the same magnitude. Now we have a head to tail connection of vector A and vector B, and then the resultant vector is the diagonal of the resulting parallelogram. So this one is good as well. And then lastly, here we have A and B added together, but this is a problem because the resultant vector is not going the correct direction. Look at this, it's going the totally wrong direction. You see, if A is acting this way, and B is acting this way, there's no way that A plus B can be going in that direction. Instead, we would expect to see that A plus B would be acting in the opposite direction. That would be a correct A plus B. So our only two options are 2 and 3, which we see here, 2 and 3 only. Okay, so here we're going to learn a little bit more about vectors in terms of their components. So if you have a person pushing a lawnmower, here you go, here's a person pushing a lawnmower. So let me point something out. Now, as the person applies the force, let's see where they're applying the force. They are applying the force from their arms, and the force is going down at this diagonal angle along the handle, right? So here is your force. A nice, strong force being pushed at a diagonal through the lawnmower. Now, this force right here is acting in two directions. It's actually acting in a vertical direction. There's a certain amount of the force that's being completely wasted because it's being pushed downward. And then there's also another part of the force that is actually acting on the horizontal. And this is the force that's being productive. This is the force that's actually pushing the lawnmower. So the greatest amount of force for the lawnmower will occur when your handle is actually lower rather than higher. So the lower you can get your handle, the more your force is going to be acting in the horizontal direction, which would be great. It would just be horrible for your back. So right here at this angle, it's kind of a nice compromise for not killing your back. But the idea here is that every time you have a force that's not completely horizontal and not completely vertical, the force is actually split into two components, and those two components are a vertical part of the force and a horizontal part of the force. And you can see here that the green is actually the the resultant, that's what I meant to say. The green is the resultant of the two component vectors. So here we're breaking apart a vector into its horizontal would be blue, and vertical components. Okay, so let's go back to the problem now. So here we have a person pushing a lawnmower with a force of 20 pounds, and the handle of the lawnmower is 62 degrees above the horizontal. So let's look at a diagram. Okay, so the green is the person pushing on the lawnmower, and the force that's applied is 20 pounds of force. And the handle is making a 62 degree angle with the horizontal. So our 62 degrees would be right here between the force and the horizontal. This is a right angle. So because it's a right angle, we have a right triangle, which means that anything we do for this right triangle is going to be SOHCAHTOA, right? How much downward force is being exerted on the ground, and how much horizontal force is being exerted? So the horizontal force, I'll call this side X, and then I will call the other side Y, and then to get the result of each of these, you just use SOHCAHTOA. So horizontal, you use cosine; vertical, you use sine. You can go ahead and try those and then see if you get the following answers. You should get this for the horizontal and this, that's for the vertical. The downward force and the horizontal force, if you use sine and cosine equations correctly, there you go. So how do these forces change? I'll let you think about this based off the discussion we already had. And of course, you can find out the correct answer if you get it wrong by repeating the homework or finding out the answer after you submit it. There's also a video here, but if you want more of the force of the handle to move the lawnmower forward, then, and I already just said this, you would want the handle should be closer to the horizontal, except the problem of that, of course, is that it's going to break your back. But that would be the ideal way of getting as much force as possible. So if you're trying to move something really heavy, and I had this experience before. I was trying to move a very heavy piece of furniture. So what I did was I got down on the horizontal with the piece of furniture, and then I used my legs at a horizontal force. I just pushed with a horizontal force using my legs to move the furniture. So, isn't that a lovely picture? Alright, so next question. A certain escalator travels at a rate of 10 meters per minute. Its angle of inclination is 28.7 degrees. So this is going to be a right triangle again. And the right triangle would be helpful if I actually had a pen here. Okay, so here's my right triangle. Now that's a fun right triangle. And this angle down here is going to be, let me just try that again. Okay, here's your escalator, and it's traveling at 10 meters per minute up here along the hypotenuse. Here's the angle of inclination. The vertical component is going to be the opposite side. The horizontal component is the adjacent side. So you use SOHCAHTOA again because it's a right triangle. Vertical component being opposite means that we use sine, and then the horizontal component is adjacent, so you use cosine. And there's a video to help you if you want to try this particular problem. Here are the answers. You've got this many meters per minute, and then this many meters per minute. Okay, so that's a first beginning intro on vectors, and next we're going to move on to some more specific word problems that require beyond your SOHCAHTOA level understanding to using law of cosines and perhaps also law of sines.